it down to the second to the lower layer. This is the layer with the Q depth, okay, which is the device driver. The default Q depth in the device driver is 128. So what we do is that we tried to change at least to 4. Of course, we could check other possibilities too, and maybe find some other findings. But let's take a look at the Q depth 4. So here again, on the x-axis, we have the combinations of scheduling algorithms with the Q depth 4, and on the y-axis, we have power in percentage. This is compared to the baseline measured with Q depth 128. So you see that there are quite interesting power values actually. So BFQ with Q depth 4, it's just like around 70% of the original default configuration. With CFQ4, it's a little bit higher, but still quite nice power consumption. What if we take a look at CF bench, so the light blue color? Well, again, it's like around 70% for BFQ4. CFQ4 is like 90%. Deadline, it's like around 90% again. All right. So it's pretty safe to say that shorter Q depth saves energy in most cases. But notice also that there are some benchmarks that don't do very well with the short Q depth, right? So in particular, for example, these two guys, that's the Smart Bench and Velamo. The main reason is that they are not storage intensive, and because the Q depth is shorter, so there is some overhead. So that's due to the overhead of smaller Q. Okay, how about cache? So if we change the cache policy to write through, so by default it's write back. When we change that, so you see again, so now we compare to the baseline with the values measured when there is a write back. So you see again that the power consumption is around like 90% of the original values. So here, essentially we can say that, again, changing the cache to the write-through seems like to consume less power. So, but then we will investigate it, and the thing is that when you want to change cache policy, it's not possible to do on the fly, as changing the scheduling algorithms or changing the Q depths. So in this case, it would require to rebuild a kernel. So that's impractical for deployment. Therefore, we didn't consider actually this part in our design. So please also refer to our paper for more details. So how can we find actually optimal configurations? You run those series of benchmarks with all combinations, very simple one, of scheduling algorithms and Q depths, and we get the optimal configurations and power savings. So looking at Entity, for example, the optimal configuration seems to be deadline. You will still remember the figure. And the Q depth, when we had the Q depth 4, it was the optimal one, and the power saving were around 40%. On the right-hand side, you also have two columns that actually show the I/O pattern. Okay, so this is still a high-level I/O pattern. In this case, it's reads per second and writes per second. Okay, so you can also see that actually there are down there two benchmarks that have 0 power savings. Why is that? Well, because the optimal configuration here is BFQ and 128, which actually is exactly the same as the default configuration. All right. Also, when you take a look at the I/O pattern, you have really few reads and few writes, which also confirms this. All right, so it's not storage intensive. Okay, so now let's take a look at the solution that we propose. It's called smart storage, and let's take a look at that. But before we approach to that, let's take a look at the big idea. As in every UbiComp idea, it has 3 steps, right? All right. So the first step, we track the phone's runtime I/O pattern. In the second step, we match the phone's I/O pattern with the pattern from the benchmark table in order to get the optimal configurations, right? And in the last step, we just dynamically configure the params in the storage subsystem. Very simple. Okay, so this is the smart storage architecture. So you can see that there is user space and kernel space. So the user space communicates with the kernel space through the netlink socket. However, the smart storage actually is a background service. So actually, no interaction with users is actually required. So this is just for advanced users and interested users. The main meat lies in the kernel space. So we have two components. One is smart storage core, and the second one is benchmark I/O patterns. So the smart storage core actually has three submodules. Okay, so we have the I/O measurement module. As it says, it actually tracks the runtime I/O pattern. Okay, and that I/O pattern is brought into the I/O matching submodule that is there further matched with the benchmark I/O patterns in order to get the optimal configurations. And then finally, we just configure the configuration in the storage subsystem. So very, very simple. So this is the GUI. On the left-hand side, we have the current status. We have scheduling algorithm in use, queue-length in use, system in use, energy save. On the right-hand side, you can see that's the tools for advanced users. Here, actually, you can the user can enforce which scheduling algorithms that the system should consider. We also have the queue length and the I/O recalculation period. All right. So we set it as 1 minute by default, but the advanced users can make play with that, because sometimes it might be better to have longer and sometimes shorter. And we also have the possibility of adding the benchmark. So how is the I/O pattern matching done actually? So what we did was that we compared the phone's I/O pattern with the patterns from the benchmark table, and we used a very simple feature. Because at the end of the day, when you have reads and writes coming to the storage, what is important is basically the rates of reads and the rates of writes. Okay, so we actually just use this simple feature. So it's rate. If the phone's rate of reads over writes per second is close to a benchmark from table, a match is found. Otherwise, there is no match. Okay. So let me show you a brief evaluation. So when we evaluate on Nexus 1, there are 3 applications with no savings actually. So which is because they have the same default configurations with the optimal configurations, BF 21.8. Let me show you Nexus 4. Nexus 4 actually reflects kind of better the state-of-the-art of flash technology now, okay? Because it's the latest, I believe latest, right? Still latest phone. So so you can see that the savings are a little bit lower than Nexus 1. Why? Because there is a new scheduler actually, CFQ, which is actually the default one in Linux kernel. So, and CFQ in our experiments proves to be the best one. So therefore, smaller savings. So average savings around 28.8%. It depends on applications, right? So let me have a brief discussion over these results. So first of all, the savings, please understand that the savings belong to the whole phone, all right? And the savings come from the optimizations on the whole I/O path, basically, right? It's not only flash, all right? So, however, how the optimizations affect CPU and other subsystems is still unknown, and we would be happy to get your feedback and your inputs and the input of of the whole research community. So with benefit, there comes also a cost, right? So we did a really, like, again, a similar experiment with applications, and it turns out that the applications have a slight delay. It's around 3%. Okay, so there's still some place to improve. Okay, so then we had another experiment in order to double check our system in the wild. Okay, so on the top figure, we have the smart storage when it is disabled. So the phone with our system when it's disabled. All right, and we run 5 applications over the length of 20 minutes. Each application for 4 minutes. And we measure the power in milliwatt again, okay? And on the bottom, the figure, we have when the smart storage is enabled. So let's take a look at the figure first. So when you take a look at these parts that I highlighted, so take a look at, for example, U2, all right? So when smart storage is disabled, the average power is, let's say, like around 1200-ish, right? Okay. When smart storage is enabled, it's around 6, 7-ish, 100, right? Okay. So that's at least it shows a little bit, right? Some information that something is going on there. So why actually after 2 minutes? Well, because the I/O recalculation, what we set was for 1 minute. And also there is some loading time, and so therefore approximately 2 minutes. Okay. Am I okay with time? Okay. So let me go to the conclusions. So we presented a study on how storage params impact power levels, and we introduced a smart storage system to save energy. Very simple. It matches current I/O pattern to known pattern from benchmarks. It gains the optimal configurations and dynamically tunes params. All right. And evaluation on top of 20 applications shows on average like 28% energy saving. So that's the conclusion. Future work. There are avenues, several avenues of future work. There is still a lot of space that we, and hopefully with help of the whole research community, we can research. So there are, of course, we can research more energy-saving opportunities with different caching policies, with different file systems, with different QDAPs. We took a look at only at 2 QDAPs, right? We can improve the matching and use the machine learning, even though our simple actually proved to be quite okay. The I/O pattern recalculation doesn't have to be just 1 minute and then that's it, or 2 minutes, that's it. But it could be adaptive. Sometimes it could be better, shorter, sometimes longer. And at the end, also we can dig in and see what are really the root reasons of the energy savings, right? So the current project status is that the US patent has been filed in December, and we welcome any licensing inquiries from industry. So we also have a small website, so where you can double check our updates on the project. And once again, I'm David Nguyen, and I thank you for your feedback, and I welcome all questions coming from all over the world. Thank you very much.
We have some time for questions. Interesting talk. I'm Sang from Nanjing University. I have 2 questions. Your project provide energy saving based on storage pattern, but do you have some experiment based on several applications running at the same time? I mean, you run the application separately, one by one. But sometimes we have the different and several applications running in the smartphone together. So how to adjust the parameter, or how to adjust the scheduling policy and other parameters to run together this application.
Yes. All right. That's a great question. Thank you very much. So what happens essentially over there is that we have BLK Trace. BLK Trace is a Linux tool that has the ability to track your runtime I/O pattern. So we actually integrated BLK Trace in our system, and based on the BLK Trace result, actually we know precisely what is the percentage of reads and percentage of writes. So there, in our tests, we try to test the applications isolatedly. But your point is valid, and we could add more applications. But essentially, what I'm trying to say is that if we add more applications, it basically creates another I/O pattern, and basically it's like one application, one complex application, and it has certain I/O pattern. Okay, did I answer your question?
Yeah.
So basically, it should be yours.
Okay, thank you.
Thank you.
The second question is, you matching the application storage pattern based on the read and write. But do you need to run one time or several times to get the statistics data?
Okay.
I mean,
Yeah, okay, I think I understand the question. So, we are trying to match, you saw that matching approach was very simple and very naive, basically. We actually just thought that what really matters is the rates of reads and rates of writes. So, in order to so first of all, the recalculation of the I/O pattern, in our case, is every 1 minute in our experiments. But actually, we can actually set up basically, if we want, it could be longer or it could be shorter. As I mentioned, in the future, probably it will be better to maybe double check if it could be adaptive somehow. Yeah. So, but the I/O recalculation is very simple. Yeah, it is very simple. When you have the percentage of reads and writes, and you compare with just the fraction, it's basically constant.
Okay, thank you very much. It's very interesting.
Yeah, thank you very much.
Hi, very nice presentation. This is Val from TU
What's your name?
Florian Val from TU.
Florian.
I have a question. So I have two questions actually. So one, is the app available already in the App Store?
So it's a background service. So first of all, and there is some unfortunately there is some negotiation process regarding the patent. So I am actually not I'm not into that process much. I am just a PhD student, unfortunately. So we have to wait, but please double check our website, and we will try to update you about that as soon as we can.
That's cool. Another thing that came to my mind is instead of periodically checking, you mentioned that for the future work, right?
Yes.
You could use maybe application switches as triggers, because usually when an application comes back into the foreground, that might be an interesting time to check.
That's actually a very good point. Yes. The recalculation could be triggered by certain events. So that's also something that we could add. That's a really good point. Yeah.
Okay,
thank you very much.
Thank you.
Hello, over here. Can Austrian University of Applied Sciences.
Yes.
What about the trade-offs? Did you study write-intensive workloads? Because when you switch from write back to write through, I expect write performance to actually half, and it might even hurt the flash because of fewer optimizations for mail leveling.
Yeah. Yeah, thank you very much. Very great, very good question. So essentially, there is also some cost, and